So today we're going to be talking about practical sources, source transformation, and maximum power transfer. Okay, so let's start by talking a little bit about practical sources. And you guys have had at least one homework assignment, but probably more, where you had these and you didn't really know what it was. Okay, so I'm going to start on the left-hand side with a practical voltage source. So anytime that we have a voltage source, I'm putting it here as an independent voltage source, but it could also be a dependent voltage source. I'm going to call this some source voltage RS in series with some resistance RS. This forms what's known as a practical voltage source, okay? So can anybody think about what the purpose of that resistor RS is in a practical voltage source? Or let me ask the question in a different way, actually. So if we had an ideal voltage source, and you don't have to write this thing down because I'm going to wind up erasing it in a moment, but if we just have our regular ideal voltage source, Vs like so, here are the terminals of the source, and then we applied a short circuit across its terminals, what would the current be that flows through the short circuit? Infinity. Now, if we were to take a AA battery and we were to connect a wire across its terminals, what would happen? Would the current be infinite? Of course not, right? Literally can't be infinite in any real or practically realizable system. So the presence of that resistance RS there is to just force the current that can leave the positive polarity terminal of our voltage source to be some finite value, okay? So this diagram right here is how we would model any real system. Okay. Now, for most batteries and things like that, the value of that source resistance is typically pretty small. So something on the order of a few ohms would actually be large. Typically, we would have something in the ballpark of milliohms of internal source resistance for a well-designed battery or well-designed DC power supply. And I can tell you emphatically that the DC power supplies that surround this room are not well-designed because their internal source resistance is almost 400 ohms, okay? I want to do an experiment to see if that has anything to do with the current limiting potentiometer. So if I open that guy all the way up, if it would lower that source resistance, but my best guess is the answer is no. They're just really cheap. And so I don't expect wonderful things out of them. But anyway, so we have a practical voltage source that is nothing more than a ideal voltage source in series with some resistance RS. And so now I want to define a couple of things here really quickly, okay? So the first thing that I want to define would be the open circuit voltage, okay? So the open circuit voltage is simply the voltage that's measured across the open circuited terminals of our practical source. So what would our open circuit voltage be equal to? Vs, right? So if we open circuit those terminals on the right-hand side, then there's definitely no current flowing through the resistor Rs, which means there's no voltage drop across the resistor Rs. So according to Kirchhoff's voltage law, the open circuit voltage VOC is simply Vs. This is the maximum voltage that we can ever get out of a practical voltage source. Okay. Now, instead of open circuiting my terminals, I'm going to short circuit my terminals, and now we're going to determine what our short circuit current is. Okay. So ISC, our short circuit current, what would that be? Vs divided by Rs. And this is the maximum current that can ever leave or be supplied to some load that is connected to a practical voltage source. Towards the end of the lecture, we're going to figure out what the maximum power will be. And just as a quick heads up, it is very much not the product of those two things. Okay. Over here on the right-hand side of the paper, let's introduce a practical current source. So in our practical current source model, we are going to have some current source IS connected in parallel with some resistance RS, like so. Okay. So what do you guys think the role of that source resistance RS is in a practical current source? So in our practical voltage source, the resistor RS limits the current. What is RS doing in the practical current source? It's limiting the voltage that could ever be achieved across the terminals of the device, right? So if I had a practical, or excuse me, an ideal current source, and again, you don't need to write this down because I am going to erase it here in a moment, but if I just had an ideal current source that is forcing some amount of current IS through this branch that effectively contains an open circuit, meaning I'm forcing current to flow where it doesn't want to, the voltage drop across that current source would be infinitely large in order to facilitate that happening, okay? That obviously can never be true. So instead, we place a resistor in parallel, and we can really quickly here see what our open circuit voltage for our practical current source would be. So what should it be? According to just good old Ohm's law, IS times RS. And this once again is the maximum voltage. And if I were to short circuit the terminals of my practical source, I would, sorry, that should be ISC. I'll get my maximum current. So what should the short circuit current be for this practical current source? IS. So all of our ideal source current bypasses that resistor RS and flows down through the short circuit. All right. So we've talked about practical voltage sources and practical current sources. They are literally just models that are used to model real systems. So real things like batteries, laboratory grade current sources, and all of that kind of good stuff. Now, let's talk about source transformation. Okay. Let me make sure I wrote that up there. Yep, source transformation. All right, so right here, I'm just redrawing my practical voltage source. Here's VS in series with RS. I'm just going to move this down a smidge because I don't like it butting into that. And I'm going to connect to my practical source some arbitrary load resistance, which I'm just going to call RL. Okay. So the value of RL is completely and utterly inconsequential for the exercise that we are about to do. Okay. So it's just a resistor that I'm interested in. I'm going to define the voltage drop across my load resistance as VL, and I'm going to define the current flowing through my load resistance as IL. And I'm going to do a similar configuration over here on the right-hand side, and I'm going to draw a practical current source, and then I'm going to apply that same load resistance across the terminals of my practical current source. Once again, defining the voltage drop across my load as VL and the current flowing through my load as IL. Now, we learned several days ago at this point about the concept of electrical equivalence, right? Just to recap, we considered two circuits to be electrically equivalent when they create the same voltage drop across their terminals, create the same current flowing through their terminals, and absorb or supply the same amount of power. So what we are going to figure out is under which conditions is a practical voltage source electrically equivalent to a practical current source and vice versa. Because what that will allow us to do is anytime we see a practical voltage source, we could replace it with an electrically equivalent practical current source if that will help to simplify our circuit. Or anytime we see a practical current source, we could replace it with an electrically equivalent practical voltage source if that will help us simplify our circuit. So this is one of the last circuit simplification techniques that we are going to learn. Okay. So what I'm going to do is on the left-hand side, I am going to figure out what VL and IL and PL, the power absorbed by my load, is. And then I'm going to do the exact same thing on the right-hand side, okay? So for our practical voltage source circuit, how could I determine the value of my load voltage, VL? It is not just VS. If it were just VS, that would be implying that effectively no current was flowing through my resistor RS, which would mean that my resistor RL would have to be infinitely large, and we have no reason to make that assumption. So we're looking for a generic case that is valid for any possible value of RL. So it could be IL times RL. I'm not discounting that by any stretch of the imagination, but I'm going to choose to express it by using voltage division so that I'm not adding another unknown quantity in here, right? So if I applied voltage division to this circuit, I would have VS times RL over RS plus RL is my load voltage. Are we all okay with that simple application of voltage division? We have a known voltage being applied across two resistors in series. So to me, this begs us to use voltage division. For our current IL, how could we express that in terms of Vs and our resistor quantities? So I think it's just Ohm's law, right? Voltage divided by the two resistors in series. So Vs over Rs plus RL. And then from this, the power absorbed by our load resistance is just going to be the product of those two quantities. So PL should just be VL times IL. So that's going to give me Vs squared times RL over Rs plus RL squared. Are we okay with this? Anybody got any questions, comments, or concerns about where any of these relationships came from? So just to recap, we did Kirchhoff's voltage law to find VL, Ohm's law to find IL, and then power is just the product of voltage and current. So let's do something similar over here, okay? So I've got a current source in parallel with two resistances. So I believe that I can determine the voltage drop across my load just by using Ohm's law. So that's just going to be IS times RS in parallel with RL, or IS times RS times RL over RS plus RL. I could find IL by applying current division. So that would look like IS times 1 over RL divided by 1 over RS plus 1 over RL. And this is actually equal to IS times RS over RS plus RL. If you guys don't believe me, I encourage you to do the very easy amount of algebra. Simply multiply the 1 over RS by RL over RL, multiply the 1 over RL by RS over RS, and you'll get that result in 2 steps. So nothing particularly wild or crazy there. Actually, we don't even need to do that. We know that 1 over RS plus 1 over RL is just RS in parallel with RL. Multiply that by a factor of 1 over RL, and you get that thing. So that's another way to do it, even easier. Okay. And from here, our power, PL, is going to be equal to the product of our voltage and our current. So that's going to look like IS squared times RS squared times RL, all divided by RS plus RL, quantity squared. All right, so under what conditions are those voltages equal to each other? Yeah, so under what condition is V sub L on the left-hand side, or evaluated for the left-hand circuit, equal to V sub L evaluated for the right-hand circuit? So for what it's worth, over here on the left-hand side, I have a factor of RL over RS plus RL. And I have a factor of RL over RS plus RL. So I just cancel those out on both sides. And what do I have left? Well, VS must be equal to IS times RS. Under what conditions are my currents equal on both sides? Notice that I have a common factor of 1 over RS plus RL on both sides. So I can scratch that out and scratch that out. And once again, I get VS is equal to IS times RS. And lastly, forcing my powers to be equivalent and seeing what cancels out, I have a common factor of RL over RS plus RL quantity squared. So that cancels that. VS squared is equal to IS squared times RS squared, or once again, no surprise whatsoever, we have the relationship that VS is equal to IS times RS. So under that singular constraint, I can transform a practical voltage source into a practical current source or a practical current source into a practical voltage source. So let's go through the mechanics of this really quickly, okay? So let's say that I had the following practical voltage source. Here, I'm going to have a 10-volt source in series with a 5-ohm resistor. This will be electrically equivalent to a practical current source. The resistance value in both of my practical sources never changes. So if I have a 5-ohm resistor in my practical voltage source, I have to have a 5-ohm resistor in my practical current source. All right, so here are the rules. If the positive polarity terminal is on top, the head of the current arrow should be on top, meaning current should be flowing up. If the positive polarity terminal of the voltage source is on bottom, then our arrow will be pointing down. If the positive polarity terminal of our voltage source is on the right, then the arrow is pointing to the right. If the positive polarity terminal of the voltage source is on the left, the arrow is pointing to the left. So whichever side gets the plus sign is the direction the arrow is pointing, okay? Using this simple Ohm's law relationship, Vs is equal to Is times Rs, it seems like our source current Is should be simply Vs over Rs. So what's 10 volts divided by 5 ohms? 2 amps. So these two practical sources are electrically equivalent to each other. So I can use them interchangeably. The load resistance does not know whether it's connected to a practical voltage source or a practical current source. It only can tell what the voltage drop across it is, what the current flowing through it is, or what its power is. And we have just proved that under the constraint Vs is equal to Is times Rs, all of those conditions are met. Fantastic question. So why do we care about this ability to transform sources? Very reasonable question. So let me make something up here. Let's call this 6 ohms. And let's make this guy over here 2 amps. All right. So I have drawn a circuit. Let's just say, for the sake of argument, our ultimate goal in this particular problem would be to determine the current Ix. So if I'm looking at this circuit, I can see that there are no resistors in series, there are no resistors in parallel, there are no current sources in parallel, there are no voltage sources at all. So there are no simplifications that I could possibly make based on all of our previous tools. If I wanted to apply mesh analysis, I count 4 meshes, which could be problematic because some of our calculators can't solve a system containing 4 equations and 4 unknowns. If I count my nodes, I have 1, 2, 3, 4, 5 nodes, which would also probably be a 4 equation, 4 unknown system. Actually, it'll wind up being 5 equations and 5 unknowns because I also have this extra thing here, Ix. So if I gave you a circuit like this on an exam, you couldn't solve this without applying source transformations. So I'm going to show you guys that within literally just a couple of steps, we can have this look like a single loop circuit that we could have analyzed on the second day of class. Okay. So I have intentionally drawn a whole bunch of terminals around things so that we can identify our practical sources. Okay. So I've got a practical current source over here on the left that I'm boxing in purple. I've got a practical current source up here in the top middle that I'm boxing in red. It does not make one bit of difference that it has a dependent source instead of an independent source. The rules still apply. And I've got yet another practical current source over here. On the right. So what I'm going to do underneath here is I'm going to redraw everything that isn't a practical current source. And then we are going to transform those other things and just see what happens real quick, okay? So here's my 10 ohm resistor. Give myself some space. Here's my 8 ohm resistor. And then down here, I literally just have a boring old short circuit, and everything else is going to be transformed, okay? So let's start with, oh, and here's my current Ix. So what would my source transformation for the practical current source on the left give me? So it's going to be a voltage source in series with a resistor 100% of the time. Because the arrow is pointed up, my positive polarity terminal should be on top. My resistor value does not change. What should the value of that voltage source be? 25, because 5 times 5 is 25 all day. Okay. Now let's work on this practical current source in the middle. Okay, so once again, I'm going to have a voltage source in series with a resistor. So here's my voltage source. Here's my resistor. My resistor value does not change, so I've just got a 3 ohm resistor. The arrow is pointed to the right, so that means the positive polarity terminal of the voltage source should be on the right. And what is 3 ohms times 3ix? 9ix. And then we can do a source transformation for the practical current source over here on the right as well. So that's going to give us a 16 ohm, or excuse me, a 6 ohm resistor in series with a voltage source. Because the arrow was pointed up, I put the positive polarity terminal on top. 6 times 2 is 12. So I have 12 volts. And this is literally a circuit that we could have analyzed on the second day of class, right? I could, for what it's worth, make some simplifications now, right? So for example, I have 25 in series with 12. They're of opposite polarities. So I could just get rid of this guy and put it as a 13-volt source. That guy gets turned into a short circuit. 5 plus 10 plus 3 plus 6. So let's see. So that's 15 plus 9 is 24. And now we have that joke of a circuit to analyze, right? So those source transformations can be used in special cases to simplify circuits. Now, I want to talk to you guys very quickly about this, okay? As we have just learned this technique, it is actually fairly limited in its application, okay? What we are going to be learning on, today's Wednesday, right? So what we're going to be learning on Friday, and then we'll be following up on the Wednesday after our exam, is what's called Thevenin and Norton's theorem, or Thevenin and Norton equivalent circuits. Thevenin and Norton equivalent circuits are just a different way to come up with practical voltage source and practical current source models for any network, okay? So what we're learning here today, we'll actually learn a better way to do something extremely similar on Friday, just to be clear. And in fact, I am actually of the opinion that this lecture is pointless, and we should have just learned that the transformation as a result of Thevenin and Norton equivalent circuits. But anyway, so at this point, we could easily analyze the circuit. So let's move on to our last topic of the day, which is maximum power transfer. And I'll need a little bit of help from you guys. Okay. So we are going to derive everything here from the perspective of having a practical voltage source. We could derive it for having a practical current source, but because we know source transformations, there's really no need to do that one as well, okay? So let's say, just for the sake of argument, that I have some practical voltage source, Vs, in series with some resistance Rs. And then I apply some load resistance across the terminals of my practical voltage source. I'm going to once again define the voltage drop across my load as VL and the current flowing through the load as IL. Now, a little while back, we came up with a relationship that for this particular circuit, the power absorbed by our load resistor, if I'm remembering correctly, should have been Vs squared multiplied by RL divided by the quantity Rs plus RL squared. I'm just going to scroll back up really quickly to make sure that I didn't make a mistake there. Okay. Vs squared times RL over Rs plus RL squared. Yep. So that's what we came up with earlier. That's what I am sticking with. So we could plot our power as a function of resistance, okay? So if on this axis, I plot PL as a function of load resistance RL, what I should get is a graph. This will be RL over here. So what I should get is a graph that looks something like this. Where this point right here represents RL is equal to 0 ohms or a short circuit. So it should make intuitive sense to us that if our load were a short circuit, the amount of power absorbed by that load should be 0. There's no voltage drop across the element, which is how we define a short circuit. Then there can't be any power absorbed by it either. Similarly, way out here as we approach infinity, so that'll be on this side, we should see that our power falls to 0 as well. Because if there's no current flowing through our load, we know that there shouldn't be any power absorbed by our load either, okay? So this graph effectively runs the gamut from a resistance of a short circuit all the way out to a resistance of an open circuit and everything in between, okay? So we can make a couple of observations here. First is that if we wanted to make sure that our resistor, absorbed some specific amount of power, for most of the points, so let's say that this was the P that we were interested in, most of the time, we'll see that there's exactly 2 resistor values that will make that work, okay? But there is one specific case where there's only one resistor value that works, and that is when our load resistor is absorbing the maximum possible amount of power. So I'm going to call this P max, and our ultimate goal here is to figure out what value of RL causes that to occur, okay? So I have a function, and I want to figure out at which value its maximum value occurs. How do I do that? Take the derivative and set it equal to 0. Absolutely right. So maximum power transfer will occur when the derivative of PL, as a function of RL taken with respect to RL is equal to 0. This is something that you guys learned way back in 241, I believe, okay? So I need to take a derivative of this thing, okay? To me, I have a function of RL in the numerator and a function of RL in the denominator, so I need to use the quotient rule, right? So just as a quick reminder here, and by all means, tell me if I'm wrong. So if I take the derivative with respect to x of, let's call it f of x, over g of x, if I'm remembering correctly, and there is a distinct possibility that I am not, because I do this math literally once a quarter, I think it comes out to be f of x times the derivative of g of x minus g of x times the derivative of f of x over g of x squared. Does that sound about right? Okay. So we're going to let Vs squared times RL be f of x, and we're going to let Rs plus RL quantity squared be g of x. All right. So let me just come over here really quickly. The derivative of PL with respect to RL should be VS squared times RL what's the derivative of RS plus RL quantity squared going to be?
Pretty sure the golden rule there, I'm pretty sure it's F prime X of X first, and then. Wow.
Where's the Google? That's why I said I was going to need your assistance, but it is definitely worth a Google. Quotient rule derivative. So F prime times G minus F times G prime. Okay, so he was correct. So we'd wind up with a negative sign, but we'll go ahead and fix that then. All right, just to make sure that we're not hand waving anything. Thank you for that. Like I said, I am very much out of practice. We'll get rid of this. Okay, so what's the derivative of VS squared times RL with respect to RL? I think it's just VS squared, right? And now we'll multiply that by our G of X, which is RS plus RL quantity squared, minus, now we need the derivative of our denominator. So I believe applying the chain rule, that's just going to come out to twice RS plus RL. Multiplied by my numerator, which is VS squared times RL. And then all of this is going to be over RS plus RL to the fourth power. If I did my derivatives correctly, which is always suspect as well. So we want this thing to be equal to 0, right? Which means effectively we just need the numerator to be equal to 0. So I'm going to throw away the denominator because it doesn't matter. Okay. So I've got a factor of VS squared, RS plus RL quantity squared is going to give me RS squared plus twice RS RL plus RL squared. Now let's see what I have here. So I've got a factor of VS squared. I'm going to pull that out as well. So I have 2 times RS times RL. And then I have 2 times RL times RL. So that should be minus twice RL squared. And set this equal to 0. Did I make a mistake in distributing things there, just to make sure? I don't think I did. But I also know that basic math is beyond me on most days, so that's why I'm asking for you guys' feedback here. Okay, so rather obviously, the VS squares on both sides there cancel out, right? I could divide both sides by VS squared and I'd still have the same relationship. I have a plus 2 RS RL and a minus 2 RS RL, so those guys go away. I have a plus RL squared and a minus 2 RL squared. So what I wind up getting is RS squared minus RL squared is equal to 0, which means that in order for maximum power transfer to occur, RL must be equal to RS. So maximum power transfer only occurs when our load is exactly equal to the internal source resistance. Okay. So subbing that value in, we can say that our maximum power, so let's just go up here. So we have Vs squared times RL. Well, we know that RL needs to be equal to RS, so I'm just replacing it there. Over RS plus RL. Once again, I'm substituting in RS for RL, so that's just going to put an RS here and square that. So that gives me Vs squared RS over 4 RS squared. So this guy right here cancels that guy right there. And we wind up just getting 1/4 Vs squared divided by RS. So that is the maximum amount of power that our practical source could ever deliver. If instead we had a practical current source, what would we do? Well, we could replace Vs with Is times Rs, and this is going to come out to be 1/4 Is squared times Rs. So just to be clear here, this is our practical voltage source, and this one is for if we have a practical current source. So let me see if I can come up with a quick example. So I've got a relatively simple circuit here. And what I want to know for this particular circuit is what value of RL will cause the remainder of the circuit to supply maximum power, and then as a second part, what is this maximum power? Okay. So effectively, our goal here is to transform everything that isn't RL into either a practical voltage source or a practical current source. So we can do this incredibly easily by simply transforming the practical current source on the left-hand side into a practical voltage source. Okay. So if let me just draw a set of terminals here. If I transform this thing over here on the left into a practical voltage source, what would that be? 30 volts in series with 10 ohms, right? Here's RL. Here's 10 volts. Here's 5 ohms. Now I have a 5 ohm resistor in series with a 10 ohm resistor, so I can just make this, shit, didn't mean to throw it. 15 ohms. I have a 30-volt source in series with a 10-volt source. They're of opposite polarities, so I can make this 20 if this one is 0. And I'll be damned if I don't already have it in a form where I can just apply my equation. So what would the answer to part A of this thing be? What's the source resistance effectively? There's only one resistor. Why is this taking so long? 15 ohms. It literally can't be anything else. If we have the circuit simplified down to a practical source, doesn't matter if it's a voltage source or current source, connected to our load resistance, maximum power transfer occurs when our load resistance is equal to the source resistance, okay? So if we have it simplified down to a practical source connected to a load, the value of the source resistance has to be RL for maximum power transfer theory to work, okay? What would the maximum power be? Literally just apply our equation. 1/4 Vs squared over Rs. So that'd be 1/4 20 volts squared over 15 ohms. I can't do that in my head. 400 over 60. 20/3 of a watt, or for you guys that like decimals, 6.667 watts. All right, so I've covered everything that I want to cover today. If you guys have any questions, by all means ask them. If not, work on your in-class assignment.